Welcome to Hot Chips 2024. Tutorial 2. The cooling of hot chips.
So we're going to start the second half, and it's going to focus on the thermal challenges in edge computing. In the first half, we looked at what's happening in the data center, and I think the message was very clear. Everybody's going to liquid cooling and all sorts of very interesting techniques that are emerging in liquid cooling. But when you come to the edge, you don't quite have the luxury of using liquid cooling. Can't imagine a consumer device, lugging along with a water pump and a cooling tower. So you got to make do with what you have. And what you have very often are heat sinks and fans. So the challenge is even bigger in edge, especially with the advent of AI and edge AI, a lot of talk about edge AI and inferencing at the edge. So we're going to have 3 speakers in the second half of this session, focus on what's happening in edge computing and how they're addressing the thermal challenges in edge computing. The first presentation is going to be from Nader Nikfar. He's a seasoned engineer with 30 years of experience in thermal management of electronics and mechanical design. Currently, he's the Senior Director of Technology at Qualcomm. At Qualcomm, he's focusing on thermal management of semiconductor packages and systems across various business units, such as mobile, compute, auto, and IoT, pretty much the entire gamut of edge computing. Nader received his BS and MS in mechanical engineering from the University of Illinois, and he has held engineering positions at Motorola, Ericsson, PowerWave Technologies, and MTI Mobile. So Nader, the floor is yours.
Thanks, Seshu. Thank you. Am I coming? Am I being heard? Excellent. Good afternoon. Thanks for the introduction, Seshu. And I also want to thank all the gentlemen that helped me to get mic'd up and resolve some technical situations here, Larry and Lance and Stefan. Good afternoon. I'm Nader Nikfar. I work at Qualcomm. My primary area of focus at company is thermal management of chipsets that we design, and subsequently they're hosting platforms that host the chipsets that we design. Today, I want to cover, obviously, the topic of on-device AI and its thermal implication. I plan to capture the content across 5 categories that I thought it was relevant in order to have a productive discussion. What is on-device AI? We'll spend a little bit of time to kind of identify, in an essence, an application of AI, an extension of AI. Then benefits and importance of it. Then we'll dive into the use cases, which I think is probably the most interesting part of this presentation, because it's the relevancy of the use cases make a major difference in the methodologies we use for cooling and also the application that can get accommodated on different platforms. Then finally, we go into the thermal stuff, kind of take a look at what implications we foresee, or we may already have, or we may not have. And then take a quick look at the potential solutions for when thermal events happen. And finally, we wrap it up with a summary. By the way, I want to disclose I'm not a computer scientist, so my AI knowledge is limited to what I had to learn in order to be able to communicate to other engineers at the company, whether they come from the power side, performance side, so I can have a productive discussion. So if you have any AI question, I won't be the one answering them. So what's on-device AI? And another disclosure. So when I talk on-device and devices on the edge, essentially the same. But one thing I want to clarify, nowadays a big vehicle is considered a device in this discussion. So it could go from little mobile, itty-bitty guys, IoT, all the way up to large robots and vehicles. They're all considered to be the device. So AI is transforming. Actually, I had AI is transforming everything, but one of the many functions at company that has to approve everything, they didn't like my phrase everything. So I just deleted it and put 3 dots. So I think what AI, I suppose, is going to transform is the way we communicate with one another, with the way we work, and with the way how we interface with the technology. So I think that probably the best way of describing it, and it doesn't get me in trouble for using phrases that are way too strong. Essentially, I guess the notion of generative AI, I look at it as across 3 categories. The perception, which is basically similar to what humans hear, talk, listen, sensory data coming, a lot of data coming from the sensors that are on devices that are on the edge, whether it happens to be your cell phone, happens to be a speaker at home, or many other devices. That's the data that is being perceived. And then later, the reasoning is mainly algorithm that analyze data, make inference, make decisions, and finally, output is the action by which the agent responds to the task in hand. So we probably spent a little bit more time on this slide. There's a lot going on here. So on-device AI and AI obviously go hand in hand. And I guess we're trying to run machine learning. Not trying, we are. Machine learning on devices like smartphone, laptops, and cars instead of cloud. There are major benefits in this, as you have already seen some implication of energy consumption complications that can go through the roof. So this is a very, very attractive compromise that you can come to results that are literally as accurate as a model that required so much energy to manage. So if you look at the slide, the illustration on the right, at the core, you have cloud AI, and you can see all these devices orbiting around. So mainly there are so many devices, medical devices, cell phones, a lot of IoT, drones, medical again. So all these devices are living on the edge, and they have an abundance of data that they have access to. So the way I also like to look at this, I like to call this guy the teacher and all the students around him. So at some point, the way the models would get optimized, that let's say a model that you could as early or as late as 2 years ago that could only run on cloud can now run on a little phone. So those models were distilled and improved in order to get to that level. The type of computing we're using at Qualcomm, we call it a heterogeneous computing here. So we obviously have had CPU and GPU for many years, and you can also notice that there are a dedicated engine for performing various tasks, whether it's audio, video, security, Wi-Fi. So you could do a lot of things just with a single CPU. In fact, we had been doing AI for several years, even on your phone, primitive kind of AI, not using a dedicated NPU engine, which is an engine that's been recently introduced by various companies, which is designed to be efficient at performing the task of AI. But in any case, we are having a heterogeneous computing here. So what happens, these, 3 major IPs will work in concert in order to achieve the best efficiency to execute and infer. Sometimes it may be that they share tasks in a way that the end results happens to consume a lot less power, and the performance is rather very attractive. Obviously, cloud The big parent remains where it's at because we're going to need cloud to train a lot of models. And that will not stop anytime soon, except it's hard to predict what future brings. And I show you some examples, but there may come a time that actually devices on edge could take over the training as well. So you don't need to constantly transmit data back and forth to the cloud. Also, one attractive thing that I almost forgot to mention, when I talk about on-device here, you have to understand, not understand, but assume you have no connectivity. You're in airplane mode, but your device in your pocket can do inference. So the model has been trained and has access to further data, but you no longer have to have connectivity. So that's a very attractive option because everybody knows nowadays, even with all the cellular infrastructure and everything else optimized, we always have trouble having a great connection, especially if it's wireless. So this makes a lot of advantage in terms of having access to doing AI without having a strong connectivity. You could have partial connectivity where a task that's supposed to complete in sub-second may complete in 5 seconds just because of a poor connectivity. So that is a really setback that you don't want to encounter because you're having such a sophisticated AI algorithm engines working, and then because of a poor connectivity, you're not able to execute on time. Some of the examples that you'll see, I mean, this becomes extremely relevant because years ago we didn't have that many gadgets. We didn't have a lot of small devices. We didn't have goggles. We didn't even have smartphones. We didn't have smart speakers, this, that. But now we have a lot of machines and gadgets that have become smart because we equip them with a processor that has processing capability and brings the smart stuff AI that's required. So I don't know, XR especially is a great example. I mean, you could talk to your XR goggle one day and, for example, I don't know, take me to a world where there are no thermal problems, you'll be there. Automotive, extremely relevant to this technology because when you go to fully automated driving, to autonomous driving, you cannot afford to make decisions by communicating to cloud. By the time the car transmits a signal wirelessly to the cloud, cloud makes an inference, transmits back to the vehicle, it's too late. But when you can do that right on the vehicle, then this becomes extremely attractive. Phones, obviously, this is the major traction because we all have phones, and this is our first line of encounter to AI. I mean, you can, I'm sure many people here use ChatGPT and things like that to generate text, generate content, generate video, generate pictures, images. So that's been, become literally it's becoming a very robust digital assistant, and it can already do a lot of stuff on such a small device without consuming that much energy that would run into a bottleneck. All this would scale over to the laptop business and PCs at such a larger order of, well, I don't want to say an order of magnitude, but imagine all the things you can do with your phone now and scale that up majorly. And on top of that, the productivity things that are related to the laptop for your work or for your personal business scales up very attractively. IoT is also a major contender because there are so many devices that fall under IoT. I think years ago, for the lack of better understanding, they decided to name it Internet of Things, and now IoT is considered a lot of things. So let's look at some of the benefits and importance. So I think this is extremely important. I don't want to say more important than thermal, but maybe just as important. Privacy. People are not comfortable transmitting their personal data, such as financial, medical, or anything, back to the cloud. It resides there. When you do it on device, it stays on the device. Your query stays on the device. The return results, whatever is infers and come back to you, stays on the device. Very attractive option for people. And also, industries, government, it is also an attractive thing for them because it's another layer of security. They're like, hey, I don't want to have your data here again. Let's just process it on your device. It's your device. You own it. It's yours. So reliability we just talked about. So that's essentially the dependency on the grid, on the wireless transmission. You're driving somewhere out in the desert, you may not have a connection, you are not very capable of doing any tasks. So that's the reliability. Low latency, extremely important. Like in XR, if the latency adds up, you could get motion sickness. In auto, the example we showed, and I'll have another one coming here, you can see that it is not affordable to have latency in order to tend to the tasks that are critical. There are a lot of tasks that may not be critical, and latency would be no problem. Imagine like an IoT device on a big ship coming across the Atlantic Ocean. Its task is every hour to transmit an abundance of data, and during that 1 hour, if that little device that's sitting somewhere potentially around 80 degrees Celsius has a small bandwidth for thermal activity, it doesn't matter how long it takes that it completes that task because nobody is waiting for that task to come in hand right away, like when you're on your phone. Cost and energy go together, so it costs money to transmit data back to the cloud. I know we all have an unlimited data package here, but when you get to the economics of it, it costs to transmit that data back to the cloud, and cloud has to transmit it back to you. So that itself is a cost element that's actually important. And energy, I mean, if you have a 10 billion parameter model and you can distill it and train it to become one, and it still returns the accurate data as you would receive with 10 billion parameters, why not go with that? And you're not having any dependency to the cloud again, and it's a fraction of energy consumption on the SoC that's within your device. Personalization, your phone is in your pocket, in your bag, it knows your habits, when you wake up, where to go, and it's all up to you how personalized you want to become with it, but it could adjust and train itself to kind of adapt to your habits and schedules and things of that nature. This was an example I mentioned. So I already noted, I'm not going to spend too much time on this slide, but it's a very latency sensitive mission when you have to make a decision. If something is in the middle of the road, in the dark, in the middle of the desert, you're not connected, you're on the autonomous driving, a decision has to be made, you're not out of luck then. Okay, use case. This is actually the interesting section I was talking about. I love this slide. A couple nights ago, I was looking at it, and I wish it would extend over here because I'm missing a part of history. But gone are the days that I could get on the internet and grab a picture and drop it there, because now 30,000 functions have to approve it. So it was already late. I had already passed my content over, but then I sat down and realized I am missing a big part of history here. And if you're as old as I am, bear with me and humor me. I wish I could have 3 more slots here. At the very left, there would be a bag phone. So I happened to be working for Motorola many years, and when the cellular phone came out, they came in a bag. So you had the electronics and a handle, and then you had a battery. Then things evolved, and the second box I'm mixing here, it became a brick phone. So now you had a brick, at least the bag is not there, everything is in one piece, no handle, I don't know, no battery, but a big handle that had everything in it. And the third one I'm missing here is the generation before we landed at StarTech. I think StarTech was introduced in 1996, and right around here, 6 years prior to that, they got rid of the bag, they got rid of the brick, and they came with a phone that was a skinny brick. If you remember again, it had a flip that covered the keyboard, and you flipped it down and you could talk on it. Of course, majority analog product, horrible in battery life. All that battery would give you 15 minutes of talk time at best. So I painted a picture that I'm missing here. 1996 we got here. Look at the size of this guy. Look at how long you could talk on it. And I'm trying to paint a story here, so I may not do it well, but I think I'm on the right track. And these are normally 6 to 7 year cadence when things changed. Then you imagine up to this point, pretty much you were just voice only. Not a good quality, horrible battery life. And then suddenly you came to this era where we keep adding features. And now you got a computer in your pocket. You know, you can do a lot with it. And who knows what's next. So the point I was trying to make with AI right now, we can look at all the use cases we want. We have numbers. It says how much it costs in terms of power to operate I don't know, some instructions or do something, but we don't know how things are going to change. There is no visible path. Nobody would have known this would happen. Who would have thought when they had a bag phone that one day you would have a computer in your pocket? They would have laughed at you. So I think in some of my slides, you see may this, may that, because we really don't know. I'm just saying we may, because there is really no clear path to where we're headed. So a little bit more about the use cases. So like I said, we've been doing AI for a while, except we didn't have a dedicated engine to do AI, but it was possible to do AI with a CPU or something else that may not be as efficient, but needless to say, the tasks were primitive enough that you could use an engine that wasn't perfected for doing inference. Takeaway message from this slide is that let's say at this time frame you were able to buy a phone and you could ask your phone as a digital assistant, hey Siri, find me this, find me that, and you know, it was all right. I mean, it didn't work all the time, but at least it was a beginning. As we go to the right, the models become very sophisticated. Now you have large language models in a span of about 7 years. You have stable diffusion where you can text and receive an image. And we're headed to a multimodal, which means all 3 modes of communication and return to your communication and request in the 3 forms: audio, video, text. Same thing, as you go right, the hardware becomes more sophisticated because you're trying to increase the efficiency. So the major advantage based on the slides we already looked, it was the efficiency. Though, who wants to put cloud to more than trouble it's already in? So in order to become efficient, you have to start getting into the microarchitecture and design dedicated engines, and you keep making them more efficient so you can do tasks that are extremely large in your pocket. Models the same. Again, we're into the multimodal, which is, you know, right now, based on today's standard, this is bad. So again, if you look at that cell phone example, we don't know how that's going to evolve. Then I strategically put a thermal arrow here. I didn't put any text or anything on it, but as everything evolves in terms of hardware use case and models, obviously your thermal legend is going to go towards red. Things are getting red. Of course, technology is not going to sit down and say, okay, it's just going to go hotter, and it is what it is. It's never going to happen. I mean, if you recall, well, CPU in the phones can do so much more than they can now, but the reason it can't is because of a thermal reason, right? They already do a lot, but let's say you want to have the most sophisticated game on your phone and game for 30 minutes. Okay, it's a problem because of a thermal, but there are a lot of techniques that make that literally transparent to the end user. Maybe at some point when a thermal event happens, we start lowering the frequency, the power consumption goes down, your graphics content may not be as rich, but you can continue gaming and you're meeting the thermal specifications of the device in terms of skin temperature, junction temperature for the silicon, and everything else. Little bit more about the use case. So here are all these different, I suppose, as far as the scientists right now can see it. Of course, this slide is a little old, but it's still pretty valid. At the top, you got cloud that's capable of doing everything from 0 to, I don't know, 1,000 billions of parameters, right? So then you look at stable diffusion models are already running. And the reason I put this line here, the 10 billion parameters right now seems to be the sweet spot for the things that after that, in the little smaller devices, you want to offset to a cloud or some larger entity. Of course, some of the laptops can deal with that already as of this year. You can see that this arrow is going to the east of the 10 billion line. So the laptops can already press that pretty good. But at some point, For tasks that are way out here, mathematical reasoning and all that, obviously that's a cloud task. But again, going back to that cell phone example, 20 years from now, this guy may be way down here. So you can run it on your phone. Okay, so we finally descend to the thermal, which is what we're here to talk about. I want to let you know that the thermal content are rather qualitative. I'm unable to bring and say, hey, when you ask ChatGPT a question and it returns an answer, how much power it burns. I wish I could do that, but I think this still doesn't take away from a productive discussion. So it's more in the context of qualitative. So the challenge of AR workload, I think we've already covered it. I'm not going to go through that much more other than a very brief mention here that, yes, we all know that if you want to do sizable enough, it's very intense. There are concurrencies, which means other things could be going on the processor or in the device itself that contributes to the heat dissipation for the system. You need things now. You can't afford to wait. This is always on. It's got to listen. It's going to be ready to execute task. On the right, we're highlighting some of the constraints for the mobile environment. Every platform would have its own constraint, depending on their size, depending on their cooling system, depending on the needs to deal with the type of model they do. Maybe if I have a simple IoT device, it doesn't need to deal with a 10 billion parameter model. It could be a very small model, and there's never going to be a thermal problem. However, these elements are extremely important. I think one of my professional colleagues, Prabhu, after me, he's going to show you a presentation, and they are trying to make a solution that continues to keep things attractive in terms of the design, the thicknesses, the dimensions. They are very important for these type of mobile devices. So the implications are absolutely workload dependent. Do I expect to run something with billions of parameters that runs on the cloud right now on a phone? No. So that is a dependency. Then thermal solution matters quite a bit. Reason I bring boundary condition is because there are a lot of industrial electronics application that they want you to run literally at 85 degrees Celsius, and they want you to stop, let's say, at 120. You got about 40 degree rise. Within that 40 degree rise, you have to do things that may not be as attractive. But when you have a phone at 25 C, you can go up to 125 C. You got 100 degree headroom, so it grants you a little bit more of a margin in order to do proper operation. Hardware configuration, I will show you some examples how much of a difference that can make. By hardware, I mean the design of the microprocessor itself, and then how the microprocessor is integrated into the rest of the system, how efficient your design is integrating the SoC to the rest of the system. I did separate. Thermal, in an essence, is hardware, but I separated it not to get lost in the translation. So that hardware configuration is extremely important, and I have some examples of what type of a differentiation it could cause. In any case, the ceiling height for this slide that we're talking about is a moving target depending on three main elements, in my opinion. Okay, so I retained the 10 billion mark here. We looked at a slide that says, okay, cloud here earlier and everything else to the left. So let's say I just make it's not an assumption, but let's say right now I want to divide the how the activities are distributed across different platforms based on their needs as well. So cloud, almost no constraints in processing power, memory, and power consumption, right? So they are privileged enough to have access to all the necessary variables to run a flawless training task or inference task, right? However, I'm not sure, given all the environmental and other initiatives nowadays, I'm not sure this is a very good argument to say, okay, I have unlimited resources to do whatever I want to do, and let's just keep going. I don't think that's a sustainable model. So when you come to the left, we consider everything here device. Phones, I believe these are headphones, smart headphones, thin glasses, PCs, IoT devices, AMRs, basically robots that run in the factories and perform various functions, and a vehicle. So here, you're no active cooling, it's off, right? So that means you have to calibrate your level of expectations on what you will see. Yes, you can distill a model that was 10 billion parameter down to 1 billion parameter, and if I only have very low single digits inaccuracy by distilling that model, but I can run in a naturally cooled environment, hey, I think people would take that as long as the inaccuracy is reasonable and doesn't contribute to a decision, for example, braking a car, no. But if it's something related to a cell phone or a query that you're trying to get an answer and you can get it in sub-seconds, hey, more power to you. So in the low and mid tier, so in the low tier you have, of course, laptops are categorized across different categories. You got thin laptops, mid tier, and performance laptops. But the gist of the story is that these guys have a knob in their hand that they can turn up. Of course, there is a limit to how much you can bump up that knob, but there is a knob that you can turn up to provide cooling. So some of these tasks that may be limited here are going to have no trouble operating here to, again, based on reasonable expectation of the three factors we just looked at, the workload, the nature of cooling system, and the hardware and all that stuff. Then you come to the mid-tier. I only put a vehicle here, so you know right now the attraction of attaching on-device AI to vehicles comes because of the fully autonomous driving, right? Even for the, let's say for level 4 and 5, you still want to have, these cars already have liquid cooling. So for level 4, level 5, and fully autonomous, they are cooling the electronics using liquid cooling. So anyhow, they have a luxury to turn that up, except within their means, because the incoming liquid temperature may not be as cool as what they see in the data center. You're in a vehicle, they might say, hey, I'll give you liquid at 75 C, and if I can operate up to 125 C, how much can you do for me? And then obviously, we already talked about the cloud, which has the largest cooling availability. Okay. I had a lot of cool videos too, but I decided not to take the chance. So I was jealous of the NVIDIA gentleman, but I think I feel safer just to go old school. This is actually a picture of the video, which our technical marketing team had prepared. This is what was presented as early as October of 23. So basically, we're claiming, not claiming, we're showing sub-second to, look at this. I mean, this is not an easy thing to do. I'm not asking, hey, show me a picture of a TV. This is saying hyper-realistic photo of a beautiful cabin inside of a forest and full of trees and plants and a large aurora in the sky. You can do that less than a second. Why go to the cloud, right? So if we already, I don't want to say AI it's in infancy, but I think maybe it's in childhood now. So as things advance, I won't be surprised that you could do a lot more than this in that level of time frame, in that time domain. But again, expectation, I keep repeating that, should be tailored to the size of the hardware and the importance of the task for that type of hardware. Okay, let's take a look at some of the solutions. So this is an important slide, and we'll get to actually look at some actual data here. So I think the efficiency of hardware is, I don't know, I don't want to rank these, but in my opinion, this is extremely important. And we already see so much traction with the improvements that are taking place in such a short span of time, 3 to 4 years. So architectural and micro-architectural design, immensely help improving the power required to complete inference. So, so I think in order to enlarge the thermal envelope and relax the thermal constraint, in addition to the power efficiency, that is the reward when you do a great job designing a great hardware. And that goes at the SoC level again, and integration to the platform. And by the way, in mobile, we've always been squeezed for thermal, for power. So the company knows how to be efficient and deal with power because we came from a mobile DNA. Of course, we've expanded into the automotive industry, auto industry, all kinds of stuff. But since we had a frame of mind with mobile, and power was the most important thing because you don't want to run out of battery in a few hours, right? So we come from the background and we take this very seriously. I think technology node improvement, I know we're running against the wall with the Moore's law coming to an end, but there's still a lot of fine tuning to be had as we head to 2 nanometer and potentially a little bit less than that. So you still get some free power saving there. We were so used to get that the last 25 years, basically every 2 years, let's say if a phone call cost you, I don't know, I'm just gonna take a number out of the thin air, don't quote me on this. Let's say if you were making a call and it's only 0.7 watts to hold a call for a long time. When you migrate to a more advanced node, that 0.7 watts becomes 0.5 watts. But what happens to that? A lot of times, like, you know, clients and others say, oh, so my junction temperature that was at 70 now should be at 65. 100% true. But feature set addition, complexity of technology, the thirst and desire for more complicated tasks to run will immediately eat up that few tenth of a watt that you said, immediately. But the result, needless to say, are extremely important. And then the model size I already talked, so distilling the models and bringing them to a level that are very manageable on edge devices is extremely important. And now, again, stressing the hardware, if you have a hardware design that's superior, this is what happens. Okay, so we run side by side, same laptops, one with our hardware, one with a competition, and we can do 5 times more performance at lower thermals because we consume a lot less power. So that's hardware pretty much. And other methodologies that have been used, by the way, I had such a nice plot, but they didn't approve me to show it, so I figured I gotta get creative and be a little bit more meditative about mitigation. So as your temperature goes up, obviously, you can start seeing, when you get to the red zone, the frequency goes down and you start ramping down in order to avoid situations that is not a complete hard stop. I know Seshu is rushing me, but this is very important. Can you give me another minute? Sure. So this is a very important architecture that we're favoring. So we're saying, we're calling it hybrid AI. So we're saying, okay, let's not run everything on the cloud, and we can't run probably everything on the edge because of the constraints of the edge devices. But how about if we have a smart protocol that can determine whatever you're trying to do, if it can determine, is the cloud needed? Okay, I'll send it to the cloud. If no, I'll just do it locally. There comes a situation that and then obviously this would evolve and become rather like a wonderful solution. So you can just kind of do, again, it's a hybrid AI. And then energy savings are still in light because elimination of round trip to the cloud, inference at much less power, and you actually help the data center guys to meet their environmental and sustainability goals. Packaging. So packaging is on question. As I said, we are resorting to more than more now. So technology is not scaling at the level it was, so there's a lot of packaging activities in order to save power. Some of these actually create more power problems, like when stacking dies on top of each other, but you do save some power consumption by doing this. You might introduce it elsewhere, but needless to say, and by the way, this is now, it's called a 3.5D because you got 2.5D, you had 3D, and then if you put the 3D on the side, it's called 3.5D. So packaging improvement are going to be very important. We continue to do research, fundamental 5 to 10 years out, platform, it fine-tunes it to the platform of choice, applied, perfects the use cases that run on that platform. So we have several teams that do that. We just don't make the processor and tell people, hey, go figure out how you can make it work. So to capture the summary, I think everything is fairly fresh because I think I rushed through the last part of it. But again, these improvements on the slide that I showed on the Delta T that it showed on the two different laptops is extremely important. This advances still would contribute, maybe not as much, but quite a bit. The models will become efficient. We bank on the hybrid AI to evolve over the near future. So I think this is where I will wrap it up. Thank you.
Thank you.
Of course.
Okay, we have time for some questions. Nader, thank you very much for a great presentation.
Of course.
I think the key point that I took away is that thermal and heat don't have to be a runaway train. Just because you want to deliver higher performance, it doesn't mean that you have to consume more power.
Absolutely.
There's
yes.
a lot you can do with hardware, optimization,
software,
algorithmic innovation, and tools improvement.
Absolutely, yes.
That you can actually maximize the performance you can deliver within a constrained thermal budget.
True.
A great point. Thank you.
Of course.
Any questions?
I'll just toss one out here because that was pretty much the point that just got made, is that you're not managing thermals so much by complex cooling solutions. You're managing thermals more down in the design details about how you're utilizing current and energy inside of your products is pretty much your approach.
That's correct. We minimize power consumption and efficiency for as much as we could, and based on our mobile DNA, we claim that we're very good at it, and we are. But sometimes, even no matter how much reduction and efficiency are already implemented in the SoC or in the chip, the task that the end user or end platform want to perform might obviously impose a large heating load. But in most of those cases, for example, vehicles, they already have liquid cooling system because they know the type of task they have to deal with. It requires a liquid cooling.
That was the question I was going to ask, is when you've got the vehicle, it seems like you've got a bigger space in order to up the performance and trade it off against cooling, because you've got the opportunity to cool in the vehicle where you don't quite the same way in other aspects.
Especially for itty-bitty devices, it is very, the constraints are very challenging.
Noted, as we've all held warm phones. Thank you.
We have another question there. Please go ahead.
Hi, can you hear me?
Yes.
Okay. So my question is regarding the kind of workloads we see on these edge devices. So they're quite different. For example, some of the computer vision workloads on classification and segmentation, they are very lightweight compared to some of the LLM kind of workloads. So do you expect that on these edge devices we'll see like a heterogeneous NPU architecture which are targeted to a specific class of workloads?
Yes, where we are right now, we seem to be happy with the heterogeneous format that we have with CPU, GPU, and NPU, right? In one of my use cases slide, you could see that within the NPU, there's already slicing going on in order to have partitions within the existing engine. So in essence, I think the answer to your question is yes.
Well, if there aren't any, we move on to the next presentation. Thank you very much, Nader.
Thank you. Thanks, Seshu. Thank you.
Okay, we're going to move on to the last two presentations, and they're going to be from startup companies. The first one is going to be from Frore Systems. The presenter is Prabhu Sathyamurthy. He's the Vice President of Engineering at Frore Systems. Before joining Frore, Prabhu was at Apple, leading the identification, evaluation, and implementation of thermal technologies, materials, and processes in product design and manufacturing of all Apple consumer electronics products. Prabhu is a seasoned entrepreneur in thermal systems engineering. He founded Amoeba Technologies to develop a cloud computing CFD platform to speed up thermal design space exploration. Prior to that, he scaled up the ice pack. No, anybody in thermal would know what ice pack is. He scaled up ice pack business from early stage to a dominant market position while he was at Fluent, which is part of ANSYS now. Prabhu has a Bachelor of Technology degree from the Indian Institute of Technology, Kharagpur, India, and a PhD from the University of Minnesota in mechanical engineering. Prabhu?
Thank you, Seshu. Hello, everyone. It's Sunday afternoon, and you are here. And thank you. This is, one second. We are starting from a wrong slide. Okay, I'm from Frore Systems. Topic today is how solid-state cooling technology is going to address some of the problems that were laid out by Nader in particular at this point in time. And then let me see if we can leapfrog from there to some of the possible solutions that Ali and Tom were talking about before that. Okay? So let's start here. Moore's law, is it dead? There's talk of this. The principal issue that we see here is that the transistors, the number of transistors in a area is increasing. So, the transistor size is decreasing. That's definitely happening. The number of transistors are going up. The power per transistor is not keeping up, especially after the 32 nanometer node. So we are now seeing that that's a retardation that is going to increase the overall power per transistor. And then, of course, you are ending up with the total heat in the system where the SoC is going to be increase. And this is a continuous problem for us. At this point in time, you need to have the thermal envelope of the system to manage what is happening with this retardation of the Moore's law that we were seeing so far. So that benefit has to be offset by proper thermal design. And I'll go further with this. To add to this, we now have an AI revolution. And we've seen a lot of discussions on this. There's a demand for higher computing in various applications. It's explosive. I mean, we see charts which are what happened 3 months ago. Now it's changed. The demand has increased much faster. How do we keep up with this? I would say that you need proper cooling, and that's the cooling of the system that is going to support this needs to be meeting that. And as Seshu mentioned, this is the edge AI devices, which is from smartphones to laptops, the thin laptops that we talk about, not the ones that are heavily cooled already, or servers and others, which of course have horsepower to cool it, right? So increasing heat and how do we manage that is our challenge. And on-device AI, what are the areas where we see the problems or where we see the applications exploding at this point in time? You see smartphones, tablets, notebooks, cameras, and especially smart cameras also in dash cam kind of environment in vehicles. These are all heavy-duty use cases that are coming in. And someone did ask a question as to what would be the power required to drive, say, an AI application in these devices. To get the full performance, or good, for instance, take the video, real-time transcription of the video with text is going to be, we've clocked it at 8 to 10 watts. Now, that's not possible on a phone. It's certainly possible on a laptop, which is cooled by a fan and a high-performing fan, right? But will we need it at the smartphone level? Very likely. If not today, the demand will push it in the coming years, if not coming months. Then there are industrial IoT devices. These are also edge devices. We see this in, where you have predictive maintenance, you have automation, robots, connected, when public transport, how the connected public transport is going to be run with smart cameras all over the place, knowing where the traffic is and maintaining it. These are all, again, edge devices that would do on-device AI, and it needs to be supported. And these could be in the 40 to 100 tops, at least, if not more. And how do we support those? In small form factors. The key here is these are not devices that can be made as big. If you remember from what Ali said, you can always cool any heat load given a certain area and a certain flow. And managing both of those together in a small compact form factor is the challenge. And here we are trying to see that in devices that are going to be, say, commercial devices, which you have in your pockets or on your dashboard, these are going to be small in form factor, but have the requirement to deliver performance. Now, I like to call this that we are seeing the tip of the iceberg of AI revolution. It just is right there. There's a lot more underneath, and certainly, I don't think we will be a Titanic at this point in time, given the amount of attention that everybody is paying to it, but managing this is going to be an interesting challenge, all right? So this is a hypothesis that we started working with, that the existing thermal solutions are inadequate. I mean, they do the job. I'm not saying that they don't do the job, but they're not doing the job enough. That there's passively cooled devices, which is, if you saw Nader's chart, everything on the left was passively cooled. That's where he was under 1 billion operations that he had. It's the smartphones, tablets, notebooks, etc. They employ simply the idea is to spread the heat and use the surface as the cooling, and that's the main thrust of the device. So if you have a size limitation, you have decided the thermal envelope. Especially when you know that you are going to touch the device, you have a touch temperature limit, you have decided that's the ceiling now. Now, how do we get past that if you have to run AI workloads? That would be a challenge. Again, those devices are, again, depending upon the size. If you look at a small laptop, a thin laptop in particular, and which is fanless, that would be up to 10 watts of SoC power, and a smartphone would be in the 3 to 5 range, okay? The actively cooled devices can go up. Their range in the edge AI world, when I say edge, in this world, it would be 15 to 35 watts, where you are doing industrial PCs, which are the small PCs that are used for many applications at the industry level, but these are not the full, either desktops or others, but they're smaller PCs, mini PCs as they're called, but run heavy AI workloads these days. Gaming laptops, gaming consoles, notebooks, which are now in the pro class, if you will, and the VR devices, and some smart cameras. These smart cameras have a limitation that they can't have fans in them. The fan vibration has a implication on smart camera usage. So now, if you have to only design based on conductive or passive cooling, the size becomes larger. Now, can you handle a large dash cam or a smart camera? That would be the trade-off. So 5 years ago, we did a thought experiment on this to come up with what is the ideal thermal solution for this space. We need a high rate of heat removal. That's a given. I mean, we need to remove the heat, and it needs to be, it has to be higher than what a passive is able to support. It should be thin. The solution itself has to be thin to fit into a compact, thin device. So it has to be thin. It has to be light in weight. You can't be making a heavy, a large copper heatsink is heavy. So now how to mitigate that and get to a thin, light solution is one. It needs to be silent. Adding a fan, cranking it up is a solution, but in the edge world, that is not an acceptable solution. Then operating efficiently in very compact devices is a critical problem. If you realize you can think of a fan. If you put it in a very compact device, the fan is actually not performing at that point. The fan's back pressure or the static pressure head will not support going through very narrow conduits to allow enough airflow to do its job. Now, the way to mitigate that would be to crank this RPM up, which is, again, going to be connected to the sound that it is going to produce. So it's going to be noisy, not a desirable solution. Now, most of these devices are also dust-proof. In the sense, currently they're sealed devices. So they're designed with the idea that nothing goes in, and it's an IP68 or a 65, 66, in that category of design. Now, any solution that one comes up with should come close to meeting that. It has to be compatible with the design, and it should meet that. And of course, reliability is a given. It needs about 4 to 5 years of operational reliability that it should meet. And scalable. I mean, this market is large. It's not like all of these markets that we're talking about, this one is many, many millions of units that would need to be made. So the solutions need to scale. So scalability is there. It's also scalability in performance. That is, you can take multiple of these units together and create a solution. So is that but it still should fit into the form factor that we are targeting, right? So the scalability in performance and the scalability in production, all of that are parts of the puzzle. Now, when we looked at this became, for at least at Frore, it became our market development or market requirements document, MRD, if you will. So I'll introduce what we did to solve this problem. We came up with a solid-state active cooling device. It's MEMS-based technology. It is 27 millimeters by 41 millimeters. So that's the size, and 2.5 millimeters thick. So that's the thickness at this point in time of our technology. It weighs about 7 grams. Now, it removes 5.25 watts of heat at a certain thermal, if you have the heat load at say 80 degrees C, and your ambient is 25, this will remove 5.25 watts of heat. The back pressure, or the pressure head of this device, is 1750 pascals. Now, 1750 pascals is like an air pump, essentially. It is an air pump. So it's a heat removal device, which is also a pump. If you compare it with fans, which would be at 150 to 200 pascals of the static pressure head, this is almost 10 times higher. And this is important because that will drive how you can put this into very compact devices and still maintain performance. You won't lose performance because you have a density of packaging is such that you can't, your system resistance, it'll handle the system resistance much, much better than a fan can handle. All right? It consumes 1 watt to remove the 5.25 watts. And if I summarize this, it is designed to make the devices fast, which is at a higher performance, SoC performance. It is quieter than fan if you are looking for a comparison. It's thinner, lighter, it's vibration-free. The way we have designed it, it is no transmitted vibrations from the device itself to exterior. So the constraint that I was talking about for dash cams and smart cameras where you cannot deploy a fan, this can address. So the whole idea here is to see how we can push the passive cooling limits with a solution which is going to do all the things that would be doable almost as a passive cooling device, but it is actually active cooling. Okay? So you're bringing active cooling into that region. Now, how does it work? That's the most important and interesting question to see. As I said, it's a MEMS technology, so it's got membranes that are there in a chamber that vibrate when the power is supplied to them. And these vibrations are at 24 to 25 kilohertz. So it's in that range. When it is vibrating at that frequency, you don't hear it. There's no physical contact in the design. So there is no stiction. So there's no noise of that emanating from the system. All right? So what happens when you power it up? This chamber design and the membrane motion is designed to create a suction. There's a pressurization of the chamber that happens. And then on the bottom side of the chamber, this white structure that you see here, there's a shower head. And that shower head creates jets to come out of that surface, hence the name air jet. So those jets are impinging on the lower surface of the device. That gap is 300 microns. So we are able to have jets which are coming out at 40 to 50 meters per second and impinge in that small gap and come out of the left-hand side. So that is the operating principle of this. And when you attach it to a processor, this jet impingement, which is one pulsating, and then it's jet impingement, is much more effective. You don't need any additional surface area to remove heat. The temperature of the exiting air is almost equal to the spreader temperature at that point. Right? So you've saturated the air with all the heat it can take. Now, the other thing that happens, which is how the jet, that's the jet coming out. This is a Schlieren image. You can see the jets coming up. As this plate was moved up, you could see how the impingement happens. And this we have stopped because for visualization, it's better to stop it right here. This goes all the way to 300 microns. Okay? And that's where the actual impingement happens. The boundary layer gets reformed every 24 at the 24 kilohertz cycle in the array underneath, and exiting air is saturated. Now that was how it works. Now how do we make this? Now in making this, we have our own fab in Taiwan, and we set it up for many reasons. One is this design is very unique. We've come up with this design which is fairly challenging design to meet what is currently available in both manufacturability and the material choices that we needed to make. So we have made a material choice here. It is semiconductor process, but not silicon. So our membranes are not silicon, as a conventional MEMS device would be. For reliability, our choice of material is different. It's titanium-based, titanium alloy. And then the processes of using semiconductor technology or processes that are there to come up with structures that are there in this membrane to meet our requirement required complete redesign of both the manufacturing processes, adapting from those available ones, but converting new equipment had to be designed. And we did all of that, and that is part of answering this question of getting to a solution that is reliable and small that fits into this paradigm. So that was how we're making it. Let me give you a brief peek at who all are using it and where it is being used right now. As I said, the aim here is to move the discussion to something that is passive, which is going to be seeing workloads which are going to be demanding, AI-driven, of course. how do they maintain sustained performance? So, but still keeping the same form factor. We don't want the form factor to change to accommodate that. So here we've shown a case where you take a computer which is ultra thin, don't change, but accommodate, say, 3 minis in this case. And what you see in the orange line here is what happens to this when it is passively cooled. You can see that it throttles immediately. It starts off at 20 watts, but it actually settles to 12 watts finally. That's the SoC performance. Whereas if you have an airjet in this same form factor, meeting almost all of the other requirements that a fanless form factor, fanless design would require, you can still maintain that 20-watt performance. The frequency remains. The SoC performance stays as it is. So this will do the job of a higher performing laptop at the same form factor. Right? Now, other place where it could go is in the premium tablet section. Again, premium tablet is because tablets are usually thin, and the premium is the thinnest ones that would be made because that's the trend that we see. And the AI device, on-device AI in that would be increasing. That's our expectation as it goes along. That is going to be a driver where the tablet and the PC, the notebook, are going to be blurred. That section is going to get blurred. And people would be expecting performance in that. We would be expecting performance in that of, say, video and video transcriptions, etc. Those are some examples, but similar. And many new applications are going to come by very, very soon. Again, in this one, you can think of the same design, and this is actually a working sample where you can drive or double the performance of the SoC without changing the form factor. Now, a fan in this situation would not perform. Today's fan. Now, and this is another actively being area where folks are looking into this, where phones, though today is staying at the passively cooled levels of 5 to 10 watts, 5 watts of performance at the most of SoC, how can we possibly increase it to something more than 5 as the demands for on-device AI grows in the coming years? One area is we already have accustomed, everybody who has a phone can see that there is a turret over the camera to accommodate high-performing cameras. We did give the leeway there for the phones. So very likely that this concept would be something that could be considered, where the slight bump in that area could accommodate one airjet mini or a cluster of mini, or one mini in this particular case. The beauty of this design is you can think of this to be IP68 compatible. That is, you can eliminate the possibility of water entering into the system, whereas the air-moving compartment is separated out. So this would be an IP68 compatible solution that can be designed, and people are working on that. So this is an active area of work. This is another area where it is being currently used, and many solutions are being developed, which is the mobile SSD. Mobile SSD, especially with the Thunderbolt coming into play, can go up to 15 watts of performance, but they're all thermally limited. That is, you see the performance of up to 3 GB per second performance for a few seconds, and then it drops. And that is not acceptable to some sections of where the storage is critical, where they would want the sustained performance be the driver. So the way to support that, and that is what this does, is having 1 or 2 minis in this would support a solution like that without, again, changing the form factor within the same form factor or making it even more compact, if you can, and get solution that meets the performance requirement, keeping the sustained performance through its full data transfer. Industrial mini PCs, both Intel-based and also NVIDIA-based ones are other areas where we see intense activity with the AirJet. Again, these have solutions which can either be with large heat sinks or heat sinks with fans on them. So those are the solutions that you can think of at the industrial PC level. Now, they are also space limited and weight limited in some cases. So AirJet is a solution, or AirJet, in general, what I would like to say as a general solution, it would be a solution that meets these requirements of being quiet, silent, quiet, thin, and be able to perform at a high flow or high thermal performance in very compact or densely packed situations. As you can see in this case, the density of packaging in this palm-sized PC is very dense, and the flow has to meet that requirement. And finally, there's the smart cities programs that are coming up all over. These cameras, again, the size of the camera currently that support the applications driving 10 watts are beginning to move towards 15, 20 watts. Again, they're going towards 40 tops to 100 tops of performance in AI. These are, again, NVIDIA-based systems. They require cooling solutions. And AirJet is a solution that we have put forth as something that will meet. And you can see that the design that is coming up with AirJet is compact, small, light, and would meet the requirements that we set forth or the customer is currently driving towards. Now, that's all discussion that we had with air cooling, moving air cooling, or bringing air cooling to what is passive sector, right? And improving the air cooling in the sections where you are concerned about not having a very high-powered fan driving the system, again, for either size or noise reasons. Now let's do an experiment to see, or a thought experiment rather, to see where we would go with water in this case. Now, nothing in our technology that we have discussed says that it needs to be just water. It can move air. The same principle of motion or membrane motions can drive water. And we can, and if we can, get the exit fluid to get anywhere close to the processor temperature, what kind of a solution would that look like? That looks to be from 5.25 watts that we are currently able to support, it ends up 22 kilowatts. Now, practicality of the solution has many questions. I completely grant you that. But this is a thought experiment. What can be possible with a MEMS technology-driven cooling solution that drives water? Now, there are many thoughts that we have and plans that we are working with, but this is an exciting area to look at going forward. Think of an active cold plate, for instance. A positive pressure cold plate. Does it help the situation? So these are some things that we are brewing, thinking through. That's something to look forward to in the coming years from our side. Any questions?
some questions? We have plenty of time for questions. So shall we start with one from Slack?
Yes, people seem very interested. We'll start with Ashwin Nanjapa from NVIDIA about the possibility of dust or coming in through your jets into the system, or if there's a filtration requirement for using this air jet.
Good question. The same back pressure or the static pressure head that I discussed would allow you to put a system dust guard. You can have a MERV 14 grade system dust guard in the system and no loss in performance. So that is certainly possible at the system level. So you can protect the system from incoming dust in that context. And for our purpose, we also have this system as it runs is a self-cleaning system. So its reliability or life is not affected by the dust because we clean periodically. So operationally, that is.
Thank you. Looks like we have a question at the speaker there.
I had a question. Is this on? I had a question about the structure of the MEMS, if you could share. Is this one layer membrane, or is this like two porous, non-hole overlapping layers operating in phase to like act like valves, or how is this thing operating unidirectionally, I guess, under vibration? I would imagine it's either like a very asymmetric waveform or a valve or something fancy. I was just curious what the mechanism is, if you can disclose that.
We can't discuss all of the details, these things, but you are right in one sense that we need to get a valve motion going without a physical valve. So there's a virtual valve creation through these membrane motions.
Okay, so it's a single membrane layer or dual?
It could be any number, actually.
Okay. Oh, thank you.
One more from Slack.
Okay, so Christoph Novak from MLID was asking, are you exploring any custom cooling designs? So you seem to have a standard product. For example, working with a smartphone manufacturer directly to integrate your cooling system to reduce thickness of the total product.
Well, it's our standard at this point as Frore. The standard product is what I just described. So that's what we are manufacturing. Now, the rest is what you call exploratory designs, and those will depend on it's a change of node, right? So it's a work that depends on the need and the.
I think it was more general.
Are we working?
It could be customized. You could.
In principle, yes.
Okay.
In principle, it can be
I think
customized.
that's more the question.
That's
Okay,
correct.
Thank you.
Yeah.
Gentleman over there.
Yeah. So my question is, during your presentation, you had various numbers with AirJet and without AirJet. So what's the source of these numbers? Are these from the real prototype or their simulation numbers?
No, these are all prototypes. These are all physical prototypes that are made and tested either by us or by customers.
Okay, and with the necessary, let's say, other system software changes as well.
Exactly.
Thank you.
It's fully operational systems, the button down, as you'd call it.
Thank you.
Question from Slack.
Yes, everybody seems to want one in their phone because that's where the questions are going here. Daesan Zhang from UCLA was asking, in a phone application, do you have any issues with drop tests? Are there any mechanical concerns about the reliability of this? We all drop our phones.
Good question. The basic drop of our system is reliable. I mean, in the regular drop test for handheld devices, etc., it is passing, and we have put it through very rigorous tests, and our customers are also putting it through them, so it is passing. Now, specifically for phones and where it is located, it's a question, but from the way it is constructed, I don't see an issue at this.
Thank you. Yes, gentleman over there.
All right, thank you. Very interesting presentation. Kevin Lam from Volantis Semiconductor. I have a couple questions. First is your active device. how much power does it itself takes?
1 watt.
1 watt. So that's not included in your 5 watts.
So the net would be 4.25 watts.
I see. And then the other thing, you show a couple other examples that shows like 12 watts or 10 watts thing. Is that means that you just make the thing bigger, or is it the same device?
It's the same device. See, all devices have a passive capacity and you have an added active capacity when you have the fan on or air jets on, right? A fan system would have a similar one. The active what I'm showing in most cases, or in most all cases, is the total SoC performance. So that includes a passive component as well in it.
I see. And finally, the thought experience with the water method is quite compelling. When do you expect it to be sampling?
Well, we will come to that. We should, if we go next year sometime, we should have a sample ready.
Can we have you come back at next Hot Chips?
Of course.
Hi, Sang-Min Lee from Puresa AI. You said that it's vibrating at high frequency, so it does not create any sound, or we cannot hear the sound. But I'm wondering, is there any vibration? So if it's a mobile device, whether you can feel the vibration?
No, you don't. There is no externally transmitted vibration. So.
Okay, thank you.
Any questions from Slack?
Yes, there was one from, Slack's moving really fast now. Is your solution currently used in any available consumer products?
Yeah, there are a couple of them that use currently.
We've got one more presentation to go, so thank you very much, Prabhu.
Thank you.
Our last presenter is Jesse Edwards. He's the distinguished engineer at Phononics. Jesse has over 30 years of experience in entrepreneurship and new product development. With more than 20 years dedicated to the development and manufacturing of traditional cooling solutions and refrigeration technologies, including solid-state, single-stage, cascade, vapor compression, Stirling derivatives, and cryogenic liquid methods. If you didn't understand all those acronyms, I'm sure Jesse is going to describe exactly what they are in his presentation. So here's Jesse. All yours.
Thank you. Sunday afternoon. Thanks for still being here. I'm really excited today to talk to you about at least one of the innovative solid-state thermal management technologies that Phononic has been developing. I am very proud to have contributed to a large majority of these developments, and I am honored to represent the entire team of extraordinary individuals at Phononic, without whom this presentation would not be possible. Who is Phononic? We're a startup, relatively small company, but we have our fingers in every piece of data that every person in this room and most in the world touch. Our products exist in data centers. Our products exist across the world in optical transceivers, stabilizing the frequencies of the lasers that we use to transmit our data around the globe. We have a truly sustainable and scalable solution that allows us to scale from microwatts at the device level all the way up to multiple kilowatts at the facilities level in HVAC applications. We have an established market leadership in a broad variety of market verticals, including optics, cold chain, and HVAC. Who am I? Team made me put this in here. I've been developing thermal solutions for over 20 years using a variety of technologies for microcooling, to multi-kilowatt tons of cooling applications using a vast variety of technologies. And I was intrigued by what Phononic had to offer, and I poured at least the last 12 years of my life into what we do at Phononic. We're here today to discuss this thermal dilemma. You've heard a lot of people talking about AI and the demand and our insatiable appetite for data and our insatiable demand for AI services. It's an exploding market, projected to grow at more than a 2x multiple over the next 6 years. But with that comes a 3x challenge in thermal management. We're demanding more bandwidth. We're demanding more compute density. We're demanding our ability to communicate across vast distances, and Phononic's technology is enabling that. But in order to do that, the data centers have to respond. They have to be able to provide not just the power, we've talked about that several times today, but also the cooling requirements needed to manage that power. And there's a significant infrastructure investment associated with that. And what does it boil down to? Every kilowatt of power that goes into those data centers, 400 watts of that power has to be managed in some way or other. Whether that's with air cooling, whether that's with water cooling, whether that's for AI services, training models, switches, we still have to manage that heat. And there's a huge growing demand in that space to not only increase the availability of data center services and AI services, but also to improve the performances that are available to us. We love all forms of heat transport. Air cooling, water cooling, our technology plays very well with all of them. So while I will be presenting a lot of data associated with air cooling, it's simply because today we're sort of at an inflection point with respect to what's required and what's available. The big problem, and I'll go into some details here to clarify, since we bridge a wide variety of market applications, is associated with these two bins of cooling technologies, air cooling, water cooling. Right now, you've probably heard at least 3 times I can say today that we are reaching the practical limits of air cooling in our data centers. And next generation power dissipations require water cooling. That's not necessarily true. It is an advantage. The problem is new data centers that have water cooling, sure, let's make every new data center water cooled. But we have a huge volume of existing data centers that rely on air cooling. And how do we manage to support legacy infrastructure, augment its capabilities, and enable the next generation? To clarify some things that I'll be talking about, we've been throwing around terms like passive cooling and active cooling. Because we bridge from device semiconductor cooling all the way up to building level HVAC, there's an important distinction between what one industry calls passive and what an industry calls active. In our case, in electronics cooling, passive cooling at the device, the server, the rack level doesn't exist anymore. That's relegated primarily to mobile or ultra-thin laptop applications. And that means conduction primarily, with a little bit of natural convection and maybe some radiation depending on the application. At the facility level, passive cooling is typically referred to as something like a cooling tower or an evaporative system or radiant-based cooling solutions. Active cooling, you see air quotes on the table there, is a little bit different. In electronics, we call passive cooling with enhanced mass flow, fans and pumps, active cooling. And at the component level, that's perfectly valid. a good way to discuss it and make sure that we don't confuse the market and the situation. But at the facility level, active cooling is very different. Active cooling, true active cooling, requires work to be done to move heat, typically against the thermodynamic forces. And that distinction falls into line with things like vapor compression, air conditioning, cracks, all of the ways in which we make our environment or our devices better, more comfortable. So I want to distinguish that because there are some very real limitations to passive cooling. Fundamentally, they are tied to ambient or sink source differentials. They're tied to the temperature around them. They can never reach the temperature around them. They will always be warmer than the temperature around them because they are passive methods. Doesn't matter if you use a heat pipe, a vapor chamber, single phase, two phase, conduction, convection, a pump, a fan, makes no difference. They're still passive and they're still limited in what they can provide. At the facility level, we've long implemented the ability to merge active cooling technologies with passive cooling technologies. You've heard this many times today. You have air cooling, maybe water cooling at the rack or server level. And then that is coupled, whether by water or air, to a cooling system, chiller, tower, vapor compression, air cooling, you name it. We like all of these cycles because, again, we play very, very well with them, but the active cooling solutions tend to overpower a device level implementation. What I mean by that is typically a device has a variable load. And if you design a system to manage a maximum load, you will tend to overcool. And that could be very, very bad in a system where you don't want free water condensation to form in that system. So effectively, you are overpowering that system and you don't have the resolution you need to be very finely controlled and responsive to the actual cooling load. That said, there might be a way. Passive thermal management and active thermal management, everybody in here better love the combination of those two because that's how everybody in here works. Liquid cooling and water cooling. Air cooling, we all use it. Our systems use it, our computers use it. But what we can do with solid state cooling, because we cut our teeth in the optoelectronic space where we are honing the thermal stability of optical lasers to maintain constant frequencies and enable significant boosts in data transmission rates without loss, we are able to dynamically respond to the load conditions of the chip, CPU, GPU, XPU, ASIC, doesn't matter. We can respond to that in a dynamic way that enables our use of passive cooling when it makes sense and active cooling when you want or need it. What do we pay in order to be able to do that? Well, basically power. Passive cooling uses a little bit of power. You've got to move those fans and pumps. But when you move into that active regime, what you do is you trade power for performance. I'll try to explain that clearly. Diagram on the left, this is a pretty typical tower-based CPU heat exchanger. This particular one, we'll get into some details later about the architecture of this and what it does. But basically, in a traditional passive cooling solution, you have a load profile, compute profile. And that profile is a function of power and frequency, typically. And as the load increases, you start out at a very high performance level, a very high frequency, high power. As you do that, you get a temperature profile. That temperature profile then drives an algorithm that tells the system, if I reach a threshold, I fold back. We've talked about it many times today, the throttling of those processors and CPUs. And this is very typical. And what this does is it creates this timeline for a compute cycle. You have a task, you submit it for processing, the computer processes that, it finishes its process, you're done. Pretty straightforward, pretty basic, passive cooling. Doesn't cost much power, pretty straightforward. But what if we can combine this passive cooling technique below the throttling limit, no power, additional power consumption, no incremental power consumption. But once we reach this processing limit, we decouple the case temperature, the die temperature, and we allow that compute load to continue to increase while we actually reduce the temperature or the thermal profile of the processor. What this does is it enables a shorter time to complete that compute cycle because we're operating at a high frequency, high power. We're crunching those numbers. And we can finish our task and start a new task and make faster training models, better capabilities at the cost of power. We only use the power we need or want when we have a demand that we can't meet with a passive solution. To try to clarify this a little bit, you start at time 0, turn your computer on, processor ramps up, power consumption ramps up. In this example, 110 watts base load. It will run at that at a throttle limit till it's done doing whatever it's doing. But when you enable dynamic cooling, you create a new paradigm. You essentially allow for an incremental increase in power consumption, but what you look at is the difference between the time passive and the time dynamic to complete the compute cycle. And even taking into account this power that you used to maintain this performance profile, at the end of the day, when you compare the passive compute profile to the dynamic compute profile, you have a net energy savings because you complete your cycle and you're no longer using that base load of energy. Properly designed, this approach can allow you to have your cake and eat it too. You can have passive functionality whenever it's possible. You can have air cooling. You can do this with water cooling. Doesn't really make much difference. We'll focus a little on air cooling today because that's sort of like the thing of the day, and that's what we're looking at in what we're doing. But remember this from before. Air cooling, water cooling, very clear limits. This is from an ASHRAE committee report that says we're sort of limited to around 400 watts with air cooling. That's true if you have a purely passive application. But if you have dynamic cooling, what you enable is an enhancement to air cooling. You increase the viability of that air cooling so that you can support significantly more total dissipation, significantly more power, compute power, not necessarily power. But at the same time, you bridge this gap. You bridge the gap between existing infrastructure, air-cooled, new infrastructure, water-cooled. You get the same advantage by decoupling the case temperature to your source and sink temperature. You enable higher temperature technical water. You enable lower cost, higher performance support infrastructure. All of this is possible if you enable this passive active dynamic functionality. Sounds great, right? Where's the meat? Phononic has actually developed, launched, and sold this product. This particular application is 3U ultra compact gaming CPU cooler. It's an all-in-one air-cooled solution that, if you look at the diagram on the right, is composed of a multi-layered, multi-function stack of a very low thermal resistance, high thermal conductivity heatsink that works just fine with no power put to it outside of the active fan until you reach your thermal limits. Once you reach your thermal limits, The tower on the right-hand side transitions from a passive mode to an active mode. The heat pump technology that's incorporated into this system decouples the base temperature, and therefore the die temperature, and allows the reject temperature to climb. MCP delta T for the thermal geeks out there. Delta T allows you to dissipate more energy. Higher delta T, more energy dissipated. Same infrastructure, same flow rate, same media. But you can pump more heat out of that system. And you can hold that temperature essentially as long as you want. It's a very straightforward and relatively simple architecture. And again, these are air-cooled towers. They don't have to be. They could just as easily be water blocks. And they would provide the same capabilities, the same functionality, and the same unique enhancement of our data center infrastructure. It's very small, very compact. It's a 92 millimeter fan, has in its entire control system, its fan, its mounting in one package, sub 800 grams. It's also very quiet, 25 to 30 dB. While, this is a kicker, it outperforms both air-cooled systems and water-cooled systems of up to twice the relative surface area. Twice the size, 240 millimeter all-in-one water-cooled CPU cooler could barely compete with this little air-cooled dynamic solution. 1U, 2U, air cooling, water cooling, doesn't make much difference. These true supply, the magnitudes vary. Water cooling is great. Mass flow is great with water cooling. This can be implemented into existing infrastructure. This can enable an extension of existing air cooling solutions without changing any of the infrastructure at the data center level. This solid state approach stabilizes the frequencies of pretty much all of our optical transceivers out there. It eliminates that throttling problem that we talk about over and over and over again, increasing the compute densities. Easily extend life by keeping those temperatures low. Increase the compute density or the power density of each rack in the system. Easily couples to water, easily couples to air. And this passive active functionality is easily implementable in a very straightforward algorithm that allows the BIOS to dynamically control. Questions?
Thanks, JC. We're super efficient with time. We'll take some questions.
All right.
Okay, any questions on Slack?
There is indeed. So Clip Young was asking, you said heat pump. This would be the active part, I guess.
Yep.
Is there something more than just the fan in the active section? What else is the detail here?
Yes, there is. Our heat pump is a semiconductor-based, not silicon, semiconductor-based thermo-electric effect heat pump system.
Oh, okay.
Effectively, it uses electron energy states to transport heat from one side of the device to the other. It is competitive to traditional vapor compression systems with respect to its capacity, performance, and costs. And it is extremely compact. Typical dimensions for these devices can range widely based on capacity, but they're usually about 2 to 3 millimeters thick. And each individual device ranges from maybe 10 millimeters up to about 30 or 40 millimeters. And those devices can be ganged together in order to enhance the capacity of the system without negatively affecting the efficiency of the system.
Can I follow up on that one?
Yes, please, go ahead.
So what's the additional power to enable this active part of the cooling?
It depends. In the example that we showed up on the screen, the incremental power to manage about 170 watt TDP CPU was about 35 watts of electrical power when you need it. When you don't need it, there's zero additional power required.
Gentleman over there.
Yes, so real quick, what is the temperature on that 170 watt TDP CPU when it's all running, and what are your approximate temperature ranges?
So it depends on whether we're doing CPU mark or floating point. But typical in our test for that particular data set that I shared with you, we were looking at between 68 and 80 degrees CPU temperature.
Thank you.
Well, thank you very much, Jesse.
Thank you.
It's been a pleasure. Well, that concludes the tutorial on thermal challenges in the AI world. So thank you very much for your time.